So up to this point, we've modeled every object we've dealt with as if it were a point particle. As an example, if we had a problem where we said that there's a box being dragged across a surface by some rope, we would start by saying we want to draw the free body diagram of that box, but of course we wouldn't treat it as a box, we would treat it as a point particle. And so we would draw in the free body diagram like this, where of course this dot that we've been drawing everything relative to represents the center of mass. What we will do in the next module is we're actually going to change the way we model objects. Modeling things as point particles, we've seen we can use that to solve numerous problems, but obviously there are some problems where the shape, size, and distribution of the mass matters. And so to start dealing with those problems, we need to start thinking about a different model that says instead of being treated as a point particle, we need to treat objects as extended objects. Now we're still going to care about the center of mass. The fundamental purpose of this video is to talk about how do we find the center of mass for any object. And so to start that conversation, we're actually going to start by looking at a series of masses. So we're going to say that we have a series of point particles. So here we've got mass 1, mass 2, and mass 3. And the fundamental question is, how do we determine the center of mass for this system? What we can do, of course, is we can draw in the vector showing us the position of each of these particles. And then the center of mass is going to be given by the mass weighted average of the position of each particle. So what does that mean? Well, basically it says that if you want to find the position of the center of mass of your system, what you're going to do is you're going to take each particle, you're going to multiply the mass times the position, you're going to add those up, and then you're going to divide by the total mass of the system. Big M here is the total mass of my system of particles. A couple things to emphasize. Fundamentally, this is still just a vector addition problem. It's just that we're weighting those vectors by how heavy the particle is that's at that position. So that's the mass weighted average piece. When we do this for a problem like this one, where we've got 3 particles in the xy plane, of course this vector equation is going to give us 2 component equations. And the first one for the x component of the center of mass is going to be take m1 times x1. So mass 1 times the x component of the position for mass 1 plus m2 x2, the mass of particle 2 times the x component of its position, plus m3 x3, the mass of particle 3 times the x component of its position. Add all that up and divide by the total mass of all 3 particles added together. That's the x component equation for the center of mass. The y component equation for the center of mass looks very similar. It's just instead of multiplying the mass by x components, we multiply the mass by y components. So this is m1 y1 plus m2 y2 plus m3 y3. Again, add all those up and now divide by the total mass of the system. What we're going to be able to do to figure out the center of mass for a system of particles is basically say, well, let's start by drawing in the vectors showing me the position of each particle, break those position vectors up into components, and now use those components in each of these 2 equations. So what if I want to think about a continuous distribution of matter? Again, we said the point of this is we want to start building up systems that give us extended objects. And so the idea here is that, well, we know that if I've got 3 objects, I know how to deal with that. Of course, if I just start adding in more objects, it doesn't change what I do, it just changes the number of times I have to do it. So the more objects I add, the more of those m1 x1 plus m2 x2 plus m3 x3 plus mass times position, however many times I have to do it, I do it once for each mass. I can keep adding masses, and as I add more and more and more masses that fill in that space, effectively at some point I've created a continuous distribution of matter. And so what we're going to do is we're going to say, well, I know how to deal with this for a whole bunch of discrete particles. The center of the position of mass is going to be equal to, again, take each chunk of mass, multiply it by the position vector, add all that up, so that's my mass-weighted vector addition, and then divide by the total mass of all the particles. In the limit that I let my chunks of mass become smaller and smaller and smaller, this summation turns into an integral. And so if I have a continuous distribution of matter, I get the position of the center of mass of my continuous distribution by taking the integral of, again, the position vector times these infinitesimal little mass elements dm. And so here's just some particular chunk of mass element dm. There's the position of that particular mass element, and then I need to just repeat this process from one end of my rod to the other. So that's the integral is going to go from one end of my rod to the other of this mass-weighted position, and then divide by the total mass of my object. Again, this is a vector equation, so I can break it up. It's going to give me an x component for the center of mass by saying, hey, I want 1 over the mass times the integral of the x value of each of these little differential elements multiplied by the differential mass element dm. I've got a y component equation, and again, it's very similar. The only thing that's changed is that instead of multiplying by the x component, I'm multiplying by the y component. And so the real question becomes, well, how do we deal with dm? Right? So what do I want to do with dm? And so in this case, let's start by looking at what we've got is we've got a line, what's known as a linear mass distribution, basically just a line of mass. And so that dm, right, this is a chunk of mass. dx is a length. So lambda here is what's known as the linear mass density. It's the mass per length of each little tiny element dm. And so if I have a uniform mass distribution, this is just going to be the total mass of my rod divided by its total length. On the other hand, if I have a non-uniform distribution, right, I might be told what this is, and it depends on where you are. So that's why this lambda, the linear mass density, is a function of position if I have a non-uniform linear mass density. But that's what I'm going to plug in for lambda. And so this dm in this case, because clearly I need to integrate in the x direction, my little differential mass elements are just lambda dx. Well, what if I change my rod? So that instead of being aligned along the x-axis, it now lies along the y-axis. I still need to think about dm, but of course dm now is not lambda dx because I don't need to integrate along the x-axis. I need to integrate along y. So by changing my rod, I've simply changed what my variable of integration is, and so dm is now lambda dy. And again, this linear mass density can be constant because I have a uniform linear mass density, so it's total mass divided by total length, or it can be non-uniform, and so it's simply something that I have to plug in that depends on where you are along the y-axis of the rod. So if instead of having a long straight rod, what if I have some sort of circular mass distribution? So here I've got a rod, but it's been bent into a circle. And so again, in thinking about dm, well, it's still lambda, the linear mass density, times some little differential length element. It's just that as I go around that circle, that length element is going to be given by r, the radius of the circle, times d theta. And so now this lets me integrate over angle as I start here and go all the way around my circle. Again, if I have a uniform linear mass density, this is still mass per length. It's just now the total length of my rod is not some length L, it's the circumference of my circle, which is 2 pi r. And again, I can have a non-uniform linear mass density that depends on the angle, depends on where you are on the rod. So how we deal with dm really depends on, well, what is our distribution of matter? How is it being distributed, so I know what I need to do in terms of thinking about some little length element that I'm going to actually end up integrating over. Well, we can play the same game if instead of having a line of mass, we have some surface of mass. So if I've got my mass spread out across some surface, say in this case it's some circular plate, then again, I've got tiny differential little mass elements. So in this case, instead of having a single integral, now I've got two because I've got stuff going on in both x and y. And notice that my differential mass element is given by sigma, this lowercase sigma, which stands for the surface mass density, times some little differential area element. So now I'm integrating over some area because my mass is now spread out over some surface. If I've got a volume, we've talked about our mass being spread along some line, mass being spread along some surface. Well, certainly we can have our mass spread out so that it takes up some volume in space, but we play the same game. So I still have my little differential mass element dm. I still want to know where its position is. So what's the position vector that takes you to dm? I'm going to break that position vector up into components. So the x component, the y component, and in this case the z component. And now with dm in each of these integrals, again I want to think about what's now rho times some little differential volume element. So rho is the volume mass density. And again, this can be constant, total mass divided by total volume, or it can be non-uniform, so that it depends on where you are within your object. So one of the other things that we want to pay attention to is, so if we've got some object that has an odd shape, what are things that we want to pay attention to in terms of thinking about this? Obviously we can go ahead and crank out the integrals and they'll tell us what the x and y components of the center of mass is. But as a general rule, we want to take advantage of symmetries within the problem. So if I look at this problem, I see that this red line, effectively if you fold this object over the red line, it's going to lie on top of each other. And so this red line is what's known as a line of symmetry. The center of mass has to be along a line of symmetry here. The other thing that I can do is if I have some strange shape, right? And so working the integral for something like this might be really complicated. What I can do is I can break my system up into pieces. If I have some continuous distribution of matter that's complicated, it might be in my interest to break that complicated object into a bunch of simpler objects, where then I can figure out where the center of mass of each of those simpler objects are. So in this case, what I might choose to do is break my complicated object up into 4 pieces. 3 of them are basically the quarters of a circle, and the last one is this little square that sits off in the first quadrant. What this does is it says, well, if you now can figure out where the center of mass is for each, I can basically turn this back into a working with point particles problem. I might be able to calculate out that, oh, I know where the center of mass is for a quarter of a circle, and I know where the center of mass is for a square, so I can figure out where the center of mass is for each of these 4 pieces that I'm breaking my object up into. I can simply go work the problem that says, instead of thinking of that as a continuous distribution of matter, I can treat it as if it were 4 point particles, one located at each position that the centers of mass of those 3 quarter circles and 1 square was. You can do the calculus, but the calculus may be complicated, it may be difficult, and it may in some cases simply be impossible to do. You want to take advantage where you can of symmetries, and you also want to take advantage where you can of breaking up your complicated object into simpler objects where the calculus may be much easier to do, or maybe even you don't need to do calculus, you just know what's going on from the geometry of the problem. So then you can effectively reduce your problem into thinking about point particles again to give you where the center of mass is for a more complicated distribution.